We will talk about, and we all know now this concept, what is distributed generation, why we have distributed generation today, and why it's a new challenge in terms of voltage control for the medium voltage. Today we are going to be focused in the medium voltage grid. We will analyze what kind of voltage control types do we have in the grid in terms of different technologies for distributed generation. We will try to describe what is this world of the medium voltage grid in terms of a Unión Fenosa company, but I think in Spain, roughly, we could say it's more or less the same in the whole territory. We will try to analyze technical analysis. Don't worry, I'm not going to give you plenty of formulas on this kind of things, so it's going to be easy. And regulatory analysis, and afterwards I'm going to present you the most important conclusions and proposals. So what the things, what are the best things, best practice that can we do in the future? So, distributed generation. What is distributed generation? We all know it's a group of generators that are connected to the distribution network, and this is the typical definition. And is that enough to say what is distributed generation? I will have to say no, because it's important to consider that we have a small installed power and should be located close to demand. So one of the most important consequences of this is distributed generation probably, in most of situations, is going to reduce losses. Or in other words, we are not expecting amounts of power injected to higher voltage levels. So wind power in Spain is not distributed generation. Okay? Because one thing is distributed generation, and another thing is wind power, that of course, yes, is distributed generation, but in Spain is so concentrated that it's not. Okay? Why do we have today distributed generation, and why we are talking about this? If we consider since the beginning of the last decade, where we were having liberalization in the electrical sector, due to the high prices, the dependence on fossil fuel, considering the environmental aspects, technological advances, security of supply, we are trying to accommodate all this distributed generation thanks to European directives and then different national laws. And distributed generation is being promoted. It's so promoted, for example, if we consider the energy balance in 2009 in Spain, we have a demand of 250 terawatts. This demand was covered by 17% of distributed generation, but basically in Spain is small hydro, combined heat and power, and photovoltaics. I'm not considering wind power because it's not distributed generation, but from renewables and combined heat and power, we have 30% of the generation covering demand, which is a quite significant figure. But if we analyze what about the installed capacity power in 2009, and if we compare with the peak, it's not here, but it's roughly 45,000 megawatts in Spain, we have like double installed capacity, so double. Can I ask is that efficient? Is what we need? It's just a reflection. What is happening when we are talking about voltage control? Finally, we are breaking the rules. Why? Because all the grids in distribution networks have been designed in a passive way. What does it mean? Basically, it's a very low monitoring level for these grids, and the flows are very predictable and only one way. If we are connected, distributed generation flows are not in one way, are in both sides, in both ways. So this is affecting the voltage profile that the grid is being designed. So we have to think, what do we have to do in order to avoid this? Because at the end, the voltage is a very important parameter to define the quality of service that we are serving to our customers. So it's an important issue. Distributed generation technologies, typical wind power, combined heat and power, solar thermal, photovoltaics, small hydro, plenty of technologies. We all know these kind of technologies, but in order to analyze distributed generation with voltage control, we have to do another classification. And basically, we have to separate these kind of technologies in terms of what kind of them have synchronous generators, asynchronous generators, or electronic devices. Because the support or the contribution in terms of voltage control is going to be completely different. These are the performance for the different technologies that we have set. For example, when we are considering electronic devices, this is the typical performance for an inverter. And I think this is the best technology of the three kind of them, because we can operate in the 4 quadrants. What does it mean? That means that if we are injecting active power into the grid, we can absorb or we can generate reactive power, what is very important, and we are going to see later on. Synchronous generator is okay, it's a typical machine, but we could have problems when we are absorbing reactive power due to stability reasons. So it's okay, we can control, we can generate and absorb reactive power, but with some restrictions. And the last one, synchronous generator, we have no controllability of reactive power, and the synchronous generator is always demanding reactive power, always. What about the grid? We've been talking about the different technologies, distributed technologies, control types for voltage control, but what about the grid? In Spain, Unión Fenosa is covering more or less 15% of the Spanish territory. We have two areas, the northwest area and the central area. We have 2 control room centers in order to control all the distribution network. Basically, we are distributing generally for more than 3 million customers. We have 360 substations, and in terms of medium voltage grid, we have to say we have roughly 35,000 kilometers of medium voltage lines, what is quite significant. But when we are talking about distribution, be careful, because distribution is not the same in all the voltage levels. And in order to understand much better why the different voltage levels are different, we have to think about what is going to be the structure of the grid, the topology. Is mesh, is radial? What about the operation type? How many assets do we have in the grid, and how many customers are demanding energy? And of course, and this is very important, how is the operation flexibility? Because the lower is the monitoring level of the distribution grid, the lower is going to be the operation flexibility. And this is one of the things that is important in terms of how can we operate the grids as active networks. Okay? So let's concentrate today in medium voltage, what basically is 20 and 15 kV in our company. And this grid is mesh or radial, depending if we are talking about urban areas or rural areas. But we are always operating these grids in a radial way. What is important? Structure could be mesh, but the operation is always radial. In this grid, there are many facets, and the operation flexibility is quite low. We will describe this with regards to the voltage control. So, in terms of the areas and the voltages, just to let you know, these are the two areas, 43% in the northwest part and 57%. But what I want to present to you is without considering the low voltage levels, the medium voltage kilometers of lines represents roughly 80% of all the kilometers. If we are also considering high voltage levels. So it's a big part of the grid. In order to study the effect of voltage control, one thing that we have done is to classify different medium voltage grades in terms of our law, what is the Ordeneco 787. This is being classified taking into account the number of customers that are connected. So we have urban areas for more than 20,000 customers, semi-urban between 2,000 and 20,000, rural concentrated between 200 and 2,000, and rural dispersed for less than 200. We have roughly more than 2,300 medium voltage lines in our company. The urban lines represents 45% between all of them. 25% are from semi-urban, and another 25 mixture, a composition between all of them. Rural are also basically 10-15% rural areas. In terms of the number of kilometers, taking into account the average length, we could say that we have the average length is very close to 20 kilometers, and this is spread from 3-4 kilometers from urban till basically 50 kilometers, where is quite variation. It's quite different. In terms of what kind of kilometers are from overhead lines or cables or underground or overhead lines, it's very obvious, this slide, because urban has a good concentration of cables, more than 80%, and in rural, of course, we have very low percent. It's very obvious, this graph. In terms of the dispersity of the medium voltage, low voltage transformers, look at this. For example, it's in urban again, it's very concentrated, the number of transformer centers, so more than 2.5. And in general, it's very close to 1.5. And here you have the installed power capacity per feeder. It's just information to you, to let you know. So, and this is the key issue, voltage control. I wasn't sure the background of the audience, so I'm not going to tell you that reactive power is like the amplitude of the oscillating power. No, don't worry. What is voltage control? The best way to understand this is with an example. Voltage control is a water tank, okay? And reactive power is water. So next time that somebody approaches you and say, what is reactive power? You can say, it's water. And everybody is going to understand this, okay? The level, the water level of this tank is the voltage level. So it's very easy. It's very important, the relation between reactive power and the voltage level. We have different taps as sources that are injecting reactive power. And thanks to this, the voltage level is increasing because water goes up. And we have some taps that are drains, that are taking out the reactive power from the tank. Okay? And between all these elements, there are some of them that are control devices for us, so we can operate with these elements in order to modify the injection or absorption of reactive power. And there are another elements that we are not able to control them, but we have to know what are they doing because they are affecting the voltage control. So when we are analyzing the voltage control, remember the voltage control is the water tank. The water tank is different for every voltage level. The size of the water tank, the taps of the water tank are not the same for 132 kV, 6645, medium voltage, that's the way we are talking today, and low voltage. So in terms of the controllability and different elements that are affecting, you can see there are some taps that we can neglect them, are not significant. So at the end, here we have the general map for the different water tanks. So in medium voltage, basically, the only thing that we can control are capacitors. And you will ask, and what about transformers? You're right. That's the another one that we are able to control. And what are doing transformers in voltage control? Connect all the water tanks. Transformers are another taps that are moving reactive power between different tanks. Okay? The size, and I put this just to put into your consideration that the higher is the voltage levels, the higher is going to be the water tank. The devices are going to inject more reactive power, they have more controllability, so it's very important, as you can see here, coordination between all the taps that are moving reactive power. Okay? So, very easy voltage control. It's not? It's not. So today we are going to be focused on medium voltage lines. As we've seen with the voltage, with the water tanks example, we have two control devices elements. The transformers with taps that basically are moving reactive power between different voltage levels, and capacitor banks that are able to inject reactive power in the grid. How are we working in the medium voltage level? With the voltage triangle design. How is that working? So here we have a medium voltage line. This is the transformer, and basically, from the distribution point of view, distribution system operator point of view, what we are doing is to fix a set point. Fix a set point, and then we are considering and we are analyzing what are going to be the scenarios in terms of valley demand and peak demand. And this is going to give us the voltage triangle. And that means that all the possible voltages that the customers are going to have. And what we have to do is to be sure that all these voltages are going to be inside the range of the law, where in Spain is a margin of 7%, upper margin and lower margin. But today, we have distributed generation. And what is happening when we are connecting distributed generation? Basically, our voltage triangle design changes. As you can see here, the new scenarios with valley demand and peak demand, now we have to consider them with no distributed generation or with distributed generation injecting power at maximum rated capacity power. So, as we can see here, we have two effects. The first one is the area is going to be different. And due to this, in this area, we can have a voltage that is going to be out of range. So the voltage triangle design that is like a passive way of thinking, because this is done in the planning purposes and studies, is not working today. What can we do? There are two effects as a conclusion here. The first one is the voltage triangle, due to the connection of distributed generation, rotates. That's the first one. And the second one is the triangle changes in angle, or in other words, the area of the different voltages that we were expecting is changing, is different. Why is that? Why is happening that? It's very important to know this, to understand this graph. This graph is coming from Seville University. We are in a project that is called REDES 2025. Also, Comillas University is involved in this project. And what we've seen is that due to the resistant reactive parameter, which is very low at high voltage grid, is telling us that when we are injecting active power in the grid, active power is becoming a very significant driver for voltage changes. And active power is not significant when we are considering high voltage. In transmission and in distribution in high voltage part of the grid, is not very significant the active power injection in terms of voltage control. And look at this. It's so important, this driver, that if we try to compensate with reactive power in order to maintain the voltage in the same level, we are going to need plenty of active power, and in some cases much more than the installed active power capacity, what is really significant. Look at this example. Here we have a 20 kV cable, and this is the voltage variation when we are injecting active power. And here we have a graph that is telling us how much reactive power do we have to inject when we are also injecting active power in order to maintain the voltage. So when we are injecting, for example, 4 megavolts of active power, we are going to need double of reactive power to maintain the voltage. So that's quite significant, because that means that in medium voltage and in low voltage, distributed generation, as it is today, is not going to be able to control and maintain the voltage in the grid. What is a quite significant conclusion. Here you have as a resume what is the ratio, because due to the extra reactive power that we need when we are talking about medium voltage. So it's very close to, for cables, very close to 2.5, and for overhead lines, 1.5. It's quite significant. How are we going on time? More or less. Okay. Here you have a real example for a urban medium voltage line where it's placed very close to Madrid, in the center of Spain, in Aranjuez. And what we have done here is, this is the feeder of the medium voltage line, and we are connecting distributed generation at the point A, B, and C, and we were checking what happens in terms of voltage control. In this first graph, we have done is for different penetration levels of this distributed generation located at the point C, where it's at the end of the feeder, you can see the first example that we were talking about before. So when we are injecting active power into medium voltage grid, the voltage profile, the voltage rises. In this case, is still more or less 3–4% up voltage. If we compare what is the impact in terms of where is located distributed generation, the farther is the distributed generation located into the medium voltage grid, the worse is going to be the impact in the voltage control in the medium voltage grid. And you can see here this example. Point C, where is the blue line, the effect is to increase the voltage much more than if we are connecting, for example, in point A, where is less variation. Comparing with the no distributed generation connection. And also, remember, we said before that active power is a much more important driver for voltage control in medium voltage than reactive power. And here you have the graph. This is the curve with no distributed generation connecting into the grid. And this red one, or magenta one, is the one when we are injecting only 1 megawatt with no reactive power. What is the biggest variation that we are finding? If we are injecting no active power and 1 megavar of reactive power, the variation is going to be less than the one with active power. So here is demonstrated that active power is a more significant driver than the reactive power. And as I resume, here you have the whole picture for the different classifications of our lines for rural, urban, semi-urban, etc., and for different penetration levels. What we're seeing today is that we have no more than 60% in our lines of distributed generation connected. So the variation in our lines, taking into account the different classifications, is up to 3%, what is quite controlled, what is all right. But the problem is, if we have more penetration levels, be careful, because the margin is going up. The voltage variation is much more significant. And the problem, in terms of regulatory analysis, is that the regulatory framework is not always helping, because there are some situations where if we are doing what the law says to us, the voltage control is getting worse and worse. We have basically three aspects of the regulatory framework. One for the transmission system operator, another one from the distribution system operator, and the last one for distributed generation. Very easy laws in general. The first one is telling the transmission system operators what are going to be the voltage ranges that the transmission system operator has to manage into the grid. And also, in this grid code, is defined all the power factors that should be fulfilled in the borders between the transmission and distribution. And this is one of the problems. And I'm going to explain why. In distribution, very easy, we have to maintain the voltage in a margin, in a range of 7%. And for distributed generation, they have to maintain fixed power factors in different time scales. So we only have a time discrimination. But this time discrimination, and we are going to remark this in conclusions, this time discrimination is for the whole country. But reactive power is a local phenomenon. I will remark this on the conclusions. One of the problems of these one of the challenges of these three regulatory framework is that there is no coordination. There is no coordination for voltage control, and this is very important. There is some coordination between the transmission and distribution, but finally, there is no coordination between distributed generator and distribution system operator. Why? Because it's the law. So we have to fulfill the law. Here you have, for example, when we have to control distribution system operators, the power factors at the borders. Power factors depends on active power and reactive power that is being injected by distributed generators. But we are not able to control distributed generators. So we are not able to control power factors. Conclusions and proposals. Technical conclusions. It's very important the relation between the resistance and the reactance, because this parameter is telling us that the active power is the main driver for voltage control in medium voltage and low voltage grids. Also, this parameter is much more significant in cables than in overhead lines. That should be considered. Voltage profile is only being raised when we are connecting distributed generation into the grid. The farther is the distributed generation from the feeder, the higher is going to be the effect in terms of voltage that is being rising. And from the passive design, in terms of the voltage triangle design, distributed generation modifies the triangle. How is this triangle modified? With a rotation and a change in the angle, or a change in the area that is covered between all these three situations. With the same penetration levels, this effect of distributed generation is higher when we have scenarios with less demand, what is quite obvious again. And the best technologies for voltage control are all of them that are able to absorb reactive power. Because remember that when you are injecting active power, you are increasing the voltage. So you need to absorb reactive power to low voltage. Small hydro and technologies with electronic devices at the moment should be the most suitable to do that. And what are the technical proposals? We need finally to apply active networks into the grid. We need coordination between the transmission system operator, between distributor generators, and the distribution system operator. How can we do that? For example, we can use new technologies that are available into the grid. We have said before that distributed generation is not going to be able to maintain the voltages within the ranges. So we need more devices, or a combination of different actions. What kind of actions? For example, we have to change the way of thinking of our set point. Our set point were fixed in the past. Probably now should be dependent on the flows in the system, as you can see in this graph. If we change this set point from here to here, probably the new area is going to fulfill again the law. So we have to change the way of thinking. What about the law? What about regulatory conclusions? Finally, we need time discrimination and location or geographic discrimination. Why? Because reactive power is a local phenomenon. But this discrimination is very important not to live as a national discrimination, because demand profiles are different in the whole country. For example, if we consider the regulatory framework that we have today, sometimes this regulatory framework is saying that we have to inject reactive power when we are in a peak demand scenario. And remember that we said that this is the action that we don't have to do. We have to absorb reactive power. So the regulatory framework in Spain is not taking into account the relation resistant-reactance and the main driver of active powers to voltage control. And in some cases, it's going in the opposite way. So what can we do? We need a regulatory framework that allows the distribution system operator, transmission system operator, and distributed generators to cooperate and to coordinate these ancillary services that is called voltage control, finally. We need to consider that reactive power is a local phenomenon, so we have to treat it as it is, taking into account the time discrimination in all the country and location discrimination in the different parts of the country. And remember, the most important conclusion today is that reactive power is water. Thank you very much. You have any question, please?
Antonio Gomez, University of Seville. I think this is a very important presentation that complements the vision we got yesterday. Somebody told us yesterday that smart grids issue is mostly related to information technology issues, but now we've seen clearly here that it's also related to grids themselves. I mean, it's, before being smart, they are grids. And this has some constraints and limitations that we should take into account. Otherwise, we don't have energy flow at all. So this is important because this is something that should be taken into account. In particular, the voltage, over voltage problem in presence of distributed generation is a very important issue. So the conclusion that keeping constant power factor is by no means acceptable nowadays, considering the capabilities of power converters that are able to control independently active and reactive power. So this is just a comment, not a question, just to elaborate.
Thank you, Antonio. There is so significant this effect. Sometimes we've been having a problem because they are maintaining reactive the power factor fixed, and in our grid in the north part of Spain, we've been having problems of very high voltage because at 8 o'clock change the valley peak to valley scenario to a peak scenario. And due to that, we have to call distributed generators to say, please do not that. And say, it's the law. I have to do this. If I do not this, I'm not going to receive the incentive scheme to receive the money. So that's the issue. So sometimes the regulatory framework is very important.
My name is Elder from the Portuguese regulator. I found your presentation very interesting, and there are some differences regarding regulatory aspects, because on one side there is some work, some mission that belongs to the distributor, to invest in different kind of network elements, not just the passive ones, but some active elements, and that's the very important part of smart grids, not just smart metering and all those information that are really important. I repeat, they are important, but it's not all. And there is a different part, which is the regulatory aspects regarding generation. And that's where the parts you just talk about, that time when all the capacitors turn on because they have to, and they have to ingest like 0.2 of the active power, and that's different parts of regulators in Portugal. A new legislation just came by, new codes for the transmission and distribution networks. Some of the issues have been treated, some unfortunately not as well. But since, like in Portugal, we have part that belongs to the government, part belongs to the regulator. And for the near future, these are going to be the aspects that have to be dealt by both the regulator and the distributors as well. So probably in the future, the investments by the network distributor operators have to be chosen carefully so that they respond to these aspects without letting to fulfill all those requirements that always have been their mission.
Okay. Thank you very much for your comments. That's right.
Sí. Sabino García Bello from Telvent. Congratulations. I would like to know what is your opinion about the parameters, the function regarding the set point, or which parameters has to be considered inside for having this set point flexible? Perhaps some information from the distribution generation.
Good question. Thank you very much. Basically, what we have done is, depending on what is happening in the grid. For example, in terms of distributed generation, we've seen that the driver that is changing the voltage variation is the active power that is being injected. So one thing that we could do is to establish a relation between the set point and the active power that is being injected by distributed generators. And with this combination, this active network way of thinking, we can accommodate the set point in the best position in order to be sure that the area of this distributed generation that is being changed for him is okay. It's okay. This is one of them. We have plenty of possibilities because we can observe the area, for example, to minimize the area, to minimize the rotation. There are plenty of works to do in this kind of analysis.